Dr. J. Marvin Herndon. We're going to talk about the Earth's inner core. Let me tell you a little bit about Marvin. Dr. J. Marvin Herndon is a scientist with a strong and yet broad background. Originally trained as a physicist, he earned a Ph.D. in nuclear chemistry and received postdoctoral training in geochemistry and cosmochemistry from world-class master scientists who had themselves learned from masters. His website, nuclearplanet.com, contains easy-to-understand descriptions of his work. The first thing you find on that website is his statement: the purpose of science is to discover the true nature of Earth and universe, and to share that knowledge with people everywhere. That's what I do, and indeed, that's what he does. 3 decades ago, Marvin Herndon began to discover that the inside of the Earth was not quite like what government-funded scientists have long thought, and quickly came to realize that scientific independence comes at a price. Since then, he has pursued science independently. Dubbed a maverick geophysicist by the Washington Post, Marvin Herndon has lived up to the moniker by providing entirely new insight into the nuclear georeactor origin of the Earth's magnetic field and into the new understanding of the way the Earth formed and works, called Whole Earth Decompression Dynamics, which provides new insight into where and why oil and natural gas deposits occur. Ladies and gentlemen, please welcome my guest tonight, Dr. J. Marvin Herndon. Good evening, sir. How are you?
Hi, good evening, and what a great introduction.
Well, thank you so much.
You've said everything. I don't have anything to say now.
Well, it's going to be a long 4 hours then.
Oh, no, I'm really only kidding. What I would like to say right up front at the get-go is that I'm open to answer any kind of questions you might have, not just about the inside of the Earth, but about what science is all about, and you know, just whatever I can shed a bit of light on. Because that statement's true. Science is about discovering the true nature of Earth and universe. And
it sure is. And
it's important to share that with people everywhere. So I appreciate the invitation to be on your program, because you're helping me do that.
Well, I appreciate what you do, and I definitely appreciate you taking time out to be with us. I've been looking forward to this. I've gone through your websites, and I'll tell you, you've got a lot of great information there. Definitely not something you can read in one night. There's quite a bit there, a lot of great information. And we're giving out them websites in the chat room as well, just so you know. And at the end of the show, I will get your links up on my websites as well.
Excellent. I appreciate that.
Oh, absolutely.
It might be a good idea to tell you how it is that I got to be to get on the path that I ended up on.
Please do.
When I was a graduate student, like any new graduate student, you know, you look at what the professors are doing and what interests you, and most of them weren't doing anything I was interested in. Except one, a chap named Marvin Rowe, Professor Marvin Rowe at Texas A&M University, and he worked on meteorites, and in fact he made some important discoveries related to meteorites, and that just seemed to click. That was the beginning, and I later came to understand why it is that meteorites are important. You know, let me explain. The people look up in the sky and see a shooting star. Well, that's called a meteor. But some of those survive their fiery entry and land on Earth. And after they land on Earth, they're called meteorites. Well, meteorites formed at about the same time the solar system formed. And they generally formed as fairly small bodies, and didn't get a lot of geological activity like the moon, for example, or the Earth.
Right.
And so some of those meteorites contain almost the original set of elements that the solar system started with, and that's like a Rosetta Stone. I mean, here you can hold in your hand something that was a very good sample of the sort of matter that the solar system formed from, minus the gases, of course. The gases like hydrogen and helium didn't get preserved. Well, so you would think that, well, gee, if you have a meteorite, you could look at it and discover that it must be like a planet, because all these things came from the same pot of matter. You know, they're just like from one big vat. And it all sounds very simple until you start looking at it, which is usually the way things are. The devil's in the details. There are a group of meteorites called chondrites that have the same elements in almost the same proportions as you can determine in the surface or in the photosphere of the sun, again, except for the gases. So because of that, we have a good sense that this is like a representative of the primordial composition from which the solar system formed. The devil in the details, though, is there are three groups of chondrites, and they're different. And this has posed a real problem. There's one big group called ordinary chondrites, and they get the name ordinary because they're the most common of the meteorites. And back in the 1930s, 1940s, people began to think, well, the Earth must be like one of these common meteorites, ordinary chondrites. And that thinking has persisted to the present. But there are two other rare type of meteorites, not nearly so common. One of them is called carbonaceous chondrites. And there's a lot of discussion about the organic matter in them and whether they might have at one time fostered life somewhere. But they, all of their elements are combined with oxygen. So we know that they can't make a planet like Earth, because we know Earth has a big, massive core.
Right.
And all of the inner planets do. So it can't be that group. There was another group. It was called instatite chondrites. And these formed under conditions where oxygen was really starved. They're much less oxidized than the ordinary chondrites. And some of the minerals aren't found, that are contained in them, aren't found on the surface of the Earth. Like a mineral called oldhamite, which is just a compound of calcium and sulfur, calcium sulfide. Well, you don't find that on the surface of the Earth. It reacts with water. So people thought, well, gee, these have strange minerals. So they're not like what's on the surface of the Earth, and there aren't many of them, so we'll ignore them. Well, ignoring things in science is kind of like bad business. So anyway, back in the 1940 or so, the idea was really sealed that the Earth was like one of these ordinary chondrites. Now, let me give you a brief sketch about what the Earth is like.
Okay.
In 1898, Emil Wiechert realized that the density of the Earth is too great for it to be made entirely of rock. See, people thought it was rock because everywhere you look is rock. Even underwater there's rock. But he realized, based on measurements made 100 years ago, that the density is too great for the Earth to be just made of rock. So he thought that maybe there's a core inside of the Earth like the iron meteorites he had seen in natural history museums.
Mm-hmm.
Well, only 8 years passed before the core was actually discovered by a seismologist, Thomas Oldham, who had actually he was studying how earthquake waves travel as they go deeper in the earth, and they seem to get faster and faster the deeper they go, up until he discovered they come to one point and then they slow down a lot. That was the discovery that the earth has a core. That was in 1906. And in the next 20 years or so, the dimensions of the core were pretty well figured out for more precise measurements, and it was found to be liquid. So the picture that came out then, say about 1930, is that the Earth was like, a big ordinary chondrite with a core. Go about halfway to the center and come to a core, and it's liquid. And people thought, well, there's nothing else there except a thin little crust on top.
Right.
Well, in 1929, there was a big earthquake in New Zealand, or near New Zealand. And when earthquake waves go through the earth, it's sort of like light waves going from one medium to the other, like from air into water, and they get bent. If you throw a penny in a swimming pool, and then you dive down to where you think it is, it's not there. Well, that's the way earthquake waves behave inside of the earth. And so there was an area on the opposite side of the earth that was a shadow zone where people thought that earthquake waves couldn't be detected. But from this 1929 earthquake, waves were detected in the shadow zone. And that was a big mystery. And the mystery was solved by a lady seismologist named Inga Lehman, who had a really neat idea. She said, okay, if there's a solid object at the center of the earth, an object just slightly smaller than the moon, when earthquake waves hit it, they can be reflected off of it, like light from a mirror, and be reflected into the shadow zone. And it turned out that she was right, and that became the inner core. That was discovered in 1936. Okay, see, this is a new discovery, and now it casts the question, well, what's the inner core made of?
That's exactly what I was going to ask you.
That was a real puzzler for scientists, and here's the reason. We know something from the meteorites and from analyzing sunlight about the abundances of the elements. Remember, we said this is sort of the primordial mixture, and they've been measured and remeasured, and so we know something about the abundances. Well, Francis Birch, a very well-known professor at Harvard, in 1940 or so, thought about this problem. And what Birch realized was that all of the meteorites that he had seen, the iron meteorites, the metal particles in the ordinary chondrites, nickel, the element nickel, is always alloyed with iron. You typically hear them spoken of as nickel-iron meteorites. And
yeah, now I've seen one of those in a museum before, a planetarium. I've seen a meteorite display, and it looked like it was iron.
Yes, well, it's a mixture of iron and nickel primarily, and this is what the core was thought to consist of. Now, Francis Birch realized that if you take all of the elements heavier than nickel and heavier than iron, and you put them all together, they couldn't make a mass big enough to account for the inner core. So, what could the inner core be? Well, the answer that Francis Birch came out with is that the inner core is nickel iron metal that is only beginning to crystallize from the melt. Okay? Like an ice cube in a glass of ice water. And so this is the idea that has gone on since 1940.
See, I always thought that there was the center of the Earth would be more like a lava of, just hot molten lava.
Well, it's an iron alloy. Is what the core of the Earth is, mainly iron and sulfur. But let me go on with this story because it gets interesting. That was 1940. And so people were thinking about this, and this became the basis for geophysics. Well, I wasn't born yet in 1940. I came a few years later. And by the time I got to be a graduate student and then a postdoc, that was in the 1970s. And everybody was in the field was anxious to study the moon rocks, the recently returned moon rocks.
Oh, yeah.
Well, I wasn't, because I figured that, this is a complex body, and you're taking a few rocks from the surface. I mean, how much can you really learn? So instead of that, I tackled the instatite chondrites, this little rare group of meteorites that had been largely ignored. And in the midst of studying them, what I tried to do was to learn as much as I could that people had published. And for example, there were some very well-known mineralogists who examined them, took pictures of them, analyzed the minerals in them. And I would spend hours on end looking at their photomicrographs, trying to understand them. And one of the things I found out is that in the 1960s, there were two discoveries made. One of them was that silicon occurs in the metal of those meteorites, unlike in all the other meteorites. And in those meteorites, there's a mineral that is a compound of nickel and silicon called, well, the mineral name is periite, but it's nickel silicide. And I thought, wow, what this means, what this told me was that if there's silicon in that alloy, it can take the nickel out. And what it would mean, and what really struck me, is that if you look at the abundance of nickel, if you could take all of the nickel out as the nickel silicide, it would make an inner core precisely the mass that it is, that's observed. And so I published this. I published that idea in the Proceedings of the Royal Society of London, that the Earth's inner core consists not of nickel iron metal, but of nickel silicide. In fact, I've almost quoted the abstract directly. And that paper was communicated by Nobel laureate Harold C. Urey. And I thought, wow, well, when this gets published, there'll be discussion and there'll be debate, and people who have laboratories will want to make measurements and verify it or refute it, and it'll be exciting times. And I got a very complimentary letter from Inga Lehman, the lady who discovered the inner core of the Earth. But then what I found to my surprise was that it was as if I had never published the paper at all. It was like silence.
Wow.
And my grants that were about other things, they all dried up. And since my university position depended on those grants, I was essentially out of a job. And that's when I realized that, if I was going to get funding from the government to do science, I couldn't make discoveries.
Oh yeah, I have always believed they hold you back, really.
Oh, it's worse than you can imagine. You know, when I was a young guy, people used to tell me things. They used to tell me that scientists don't tell the truth, and that they don't work on certain problems. And at the time, I thought, nonsense. You know, a real scientist wouldn't do that.
You would think, huh?
I'd still tell you a real scientist wouldn't do that. But believe me, there are a lot of people who call themselves scientists that do that exact same thing. And you can find them all the way from the bottom up to the top, members even of the National Academy of Sciences that do that. So basically, I found myself in a very strange position. I was on to something really important. And so I decided I just wouldn't put it down. And I kind of worked on the problem part-time while I did other things to make a living. But pretty soon, the pieces began to fall in place. See, if you're in science, things are logically and causally related. So if you are at one point and you're right about what you've discovered, it very likely will lead you to another point. And if you're right about that, it'll lead you to another point. On the other hand, if you're not right, then you don't get anywhere. It's like being in a blind alley. And I think I was on the right track because I had learned what good science is all about and how to connect observations to the abundances of the elements and to the properties of matter, and to really anchor them securely there. So that began my adventures about learning about the Earth. Is this too boring for you? Michael? Hello? Michael? Hello?
Yes, Dr. Herndon, Michael seems to be having a few problems.
Okay, yes. I'm back. I don't know. It said that one of my colleagues had actually entered in as the host and kind of knocked me off, so I don't know what happened. Definitely a switchboard error. I apologize for that. Thank you, Nova.
You're back then.
Yes, I am back. I'm sorry about that. Yeah, I got knocked off. For some reason, I got muted, but we fixed the problem, so apologize for that.
The reason I found out, I was busy talking, and I asked you if this was boring.
Oh, absolutely not. And I heard everything you said. I just couldn't speak back. So.
Oh, okay. So we're back online then.
Yes, sir. Yeah, you've actually never left. It was me who did. So.
All right. Shall we continue?
Yes, sir. Please.
Okay. So I looked at the instatite chondrites, those special rare meteorites, and I saw nickel silicide, and I said, okay, there's good reason that could be the inner core of the Earth. Well, after a conversation one night with Inga Lehman, very stimulating conversation, my brain was alive, and I started thinking, look, if the inner core is really nickel silicide, then the core of the Earth must be like the alloy part of an instatite chondrite. And then it must be surrounded by a shell of silicate rock, like the silicate of the instatite chondrite. And so I did some really simple calculations, and I only used the ratio of the alloy to silicate of an instatite chondrite and the mass of the Earth's core, and I calculated what the mass of that shell should be. Then I went to tables where these mass distributions inside of the Earth are shown, and it turned out that the boundary that I calculated was within 1.2% of a major seismic discontinuity that separates the upper mantle from the lower mantle. So this was further evidence, and in fact very strong evidence, that the inner 82% of the Earth, at least, is like an instatite chondrite, not like an ordinary chondrite as thought by Francis Birch, and had been thought that way already then about 40 years. So here is what it all means. There's a real difference between an ordinary chondrite and an instatite chondrite, and the real difference comes about for one reason. It has to do with the amount of oxygen. See, in the ordinary chondrites, any of the elements that like oxygen are combined with it. In fact, there was enough oxygen that even some of the elements like iron are partially combined with oxygen. Whereas in the instatite chondrites, oxygen was so starved during formation that some of the elements that really, really love oxygen couldn't get enough. Elements like silicon, like magnesium, like calcium, like uranium, and they then ended up in the core of the Earth. Well, it took some years later before I realized what the significance of that was. People had thought all the uranium was in the surface, in the mantle or in the crust, in the silicate. But I realized that a large part of the Earth's uranium was in the core. Now, deep inside of a planet, the density, how dense something is, only really depends upon the atomic number and the atomic mass. So uranium, having the highest of both of those, would be the densest substance and would tend to accumulate at the center of the Earth. And this was really the basis for understanding the possibility of a nuclear reactor at the center of the Earth.
Okay, now it gets interesting. That's exactly.
now it gets interesting, and there's almost a little story about that. Back when I was a graduate student, I was in the lab, and Marvin Rowe, my thesis advisor, came in really excited to tell me something. His thesis advisor, Paul K. Kuroda, in 1956 had predicted that thick seams in uranium mines might have 2 billion years ago might have acted like natural nuclear reactors and started a chain reaction. And when he published that was very unpopular. In fact, Kuroda later told me that the only reason he could get it published at all was that he knew of one journal that would publish papers less than a page long or without reviews. Well, people ignored that paper until 1972. And I'm not quite sure how this happened. You hear different stories, but uranium ore, the isotopes of uranium, U-235, U-238, are very constant in nature. And so, I mean, it's predictable. You take uranium that you mine in South Africa, and it's the same as uranium you might mine in Utah, something like that.
Right.
But French scientists made a discovery, And the discovery was that in some shipment of uranium ore from West Africa, the fissionable uranium, U-235, was depleted somewhat. And they didn't ignore that at all, because I think they were afraid someone was stealing it. So they did a really good, thorough detective job going back each step along the way, and they traced the problem. They traced the loss of uranium right to the mine in Africa, where they discovered the intact remains of a natural nuclear reactor that had functioned 2 billion years ago. That's 2,000 million years ago.
That is amazing.
Just like Kuroda had predicted. And this is called Oklo. The area in the Republic of Gabon is called Oklo. And that took a little while to get the story out, but it's starting to be in textbooks now. Well, when Marvin Rowe ran into the lab to tell me about this, he was very excited, because as soon as the French had discovered that, they contacted Kuroda. And of course, Kuroda contacted his students, and his student, Marvin Rowe, then told his student, Marvin Herndon, about the discovery. Well, I remember thinking at the time, this is absolutely fantastic, and it's got huge implications. But I remember trying to think through the implications, and it was like looking out into a fog. You could see that there must be something out there, but it was just not clear. There were too many unknowns, too many missing pieces. Well, I didn't realize it, but over the next 20 years, I was unconsciously filling in those missing pieces. One day, about 1990 or so, one of my sons had bought a book, or I guess he had been given a book, about planets. And he read that Jupiter radiates more energy than it receives from the sun. Jupiter has a very powerful internal energy source. So he showed me this, and I really wasn't aware of it, I guess. I was interested in other things. But the excuses or the explanations that were given by scientists for that just didn't make sense to me. I mean, one scientist said, well, you know, they've looked at all the possibilities, and it can't be any of those. It can't be chemical energy. It can't be thermonuclear fusion. Therefore, it's energy left over from when the planet formed. Energy left over from when Jupiter formed 4.5 billion years ago. Well, Jupiter
and that's not the case, is it?
No, Jupiter is 98% hydrogen and helium. You can't find a better heat transfer medium than that. So, I mean, any heat that would have been would have left. So I was pondering that. And this was interesting, because about a week later, you know, I'm mulling these things over in my mind, and I went to the grocery store, as we all do, and all of a sudden it hit me. It was like a lightning bolt. Jupiter has all of the ingredients for a natural nuclear reactor at its center. And so I came back very excited and started doing the calculations and similar calculations that Kuroda had used to predict the reactors at Oklo. And in 1992, I published that as the energy source, the feasibility of a nuclear. Well, in 1992, I published it for the giant planets, feasibility of nuclear reactors as energy sources for the giant outer planets. And at the time, I was thinking, well, you know, the nuclear reactors typically, many of them use hydrogen to slow, or some moderator like carbon or deuterium to slow neutrons to much slower energies so that they can more efficiently fission. Well, when I wrote that paper, I just assumed that it was hydrogen was the moderator, and I showed that it would do it. That the compound UH3 was a perfect combination of fuel and moderator, and so it all worked out. But then, just about the time it was published, I got to thinking, well, what would happen if the heat broke apart the uranium hydride molecule? Would the reactor shut down? And it didn't take long to figure the answer. No, it wouldn't shut down at all. You'd have a fast neutron reactor. It wasn't necessary to slow the neutrons at all. Well, that then was the one bit of information that allowed me to go to the inside of the Earth with the thought of a nuclear reactor there, because I already knew that there was uranium in the core, and I had a good reason that the uranium should have gone to the center. And the uranium wouldn't need any moderators, any hydrogen or anything to slow the neutrons. It would be a fast neutron breeder reactor. And so in 1993, I published that as the feasibility of a nuclear reactor at the Earth's center as the energy source for the geomagnetic field. And that was the first of a number of publications over the next, what's it been now, 18 years? Concerning, and each step, improving the knowledge. And the idea at first was that this would just produce heat to drive the mechanism that produces the Earth's magnetic field, which I probably need to get into just a little bit before continuing. Am I getting too deep into this stuff?
Oh, absolutely not. But, I have to ask, now, if the core of the Earth is, as you call it, a georeactor, does that mean that we're really sitting on a time bomb here? Could it blow up?
No, actually, first of all, it's not the core. The core of the Earth is 10 million times as massive as the georeactor. A georeactor is just a small object, maybe 10 miles in diameter at the very, very center.
Okay.
And one thing I've come to learn is that there's a built-in mechanism for self-regulation. There's certain kinds of nuclear reactors that can't run wild. One of the modern ones is the pebble bed reactor. And if it starts to get out of control, it shuts itself down. Okay, so
Okay.
there's a balance, and this is the way it works in the georeactor. Think about this. Imagine that you have a sphere, and it's got fission products, and it's got uranium in it, and the sphere is in almost zero gravity, very microgravity, not without, but just microgravity. And so the uranium, picture the uranium as settling out to the center. And as it settles out to the center, it starts to undergo chain reactions. A nuclear reactor is just a ball of uranium. Nothing more complicated than that. You see all the plumbing and so forth in a reactor. That's just to control it so it doesn't run wild. All the cooling and that sort of thing. And so if you picture a ball of this fission products and uranium and the uranium coming out to the center, and producing heat. And the heat keeps that ball circulating in motion. And so if there's too much heat being produced, some of that uranium in the center is going to go join the ball, and it'll shut down and won't be part of the reaction.
Oh, okay.
And if the fission slows down, it gets cooler, more uranium will settle out. So it's just like self-regulating. And so that's I think the reason we don't have to worry about the georeactor exploding or anything like that. But
okay, because when I think of it, I think of like a say a nuclear power plant or such, and you know, they can have an accident and it could explode, and that's why I wondered if possibly it was.
That's a good question, and this is what it really comes down to. The nuclear power plants, most of them that you know about, have cooling systems to take the heat away, and they use that heat to produce steam to drive dynamos to make electricity.
Right.
But they have to control the reaction. They have to control the flow of water. It's a delicate balance that has to be maintained, and if you don't maintain it, you get a problem like they had at Chernobyl. Well, there are modern reactors that have been designed that are much safer. In fact, there's a company that is marketing, I don't think they've produced any yet. They've apparently taken orders for some little small reactors that would be about the size of a hot tub. And they would produce energy for about 5 years without refueling, and would be totally safe. They couldn't run wild. And I forget how many homes they could power. I don't remember the number, whether it's 1,000 homes or whatever. But I mean, this is sort of the wave of the future. And so the georeactor, in a lot of senses, is like that. It's not something that you have to worry about exploding.
Okay, that's good news.
Yeah, well, you have to be concerned about those things.
Does it pose any dangers at all to life? I mean, can...
Oh, no, we are so shielded. You're shielded by 2,000 miles of iron alloy, and then another 2,000 miles of rock. So we are totally safe from the radiation.
Well, it's almost like so much intelligence went behind the creation of not only the planet, but so many other things, just life in general. I mean, you think about it, with that in the center of the Earth, and then all the iron and protection that you just mentioned. It's just amazing. It just seems like intelligence.
All of these things are connected in a way. I mean, if there was a nuclear reactor that was just flooding the Earth's surface with radiation, then there'd never be any life on Earth. You see, everything sort of has to work together, and that's actually a comforting thought. And so this is part of the feel of science when you're making discoveries, and the discoveries are correct and they're well founded. They work because they relate to other things. Now let me if I may get into the story about the Earth's magnetic field.
Okay.
We all know about the Earth's magnetic field. It's what makes compass needles point north and south, and it's what protects the Earth from the onslaught of the solar wind, deflecting it around and past the Earth. Well, the Earth's magnetic field has been a great mystery for a long time, how it was generated. It said that Einstein thought that that was one of the greatest unsolved mysteries, the most fundamental problems that was totally unsolved. And in 1939, a geophysicist named Walter Elsasser had an idea. And it was based on an idea that somebody had published about a way for magnetic fields to occur on the sun. And what Elsasser thought is that the Earth's fluid core was convecting. You understand convection, right? You heat from the bottom, it goes up, it cools, it comes down. Well, he had the idea that the Earth's magnetic field was convecting, that it was an electrical conductor, and that convection motion was twisted by the rotation of the planet. And the net result was that the combination of that twisted rotation acted like a dynamo, like a magnetic amplifier. And this is what people have thought for many years generates the Earth's magnetic field. Well, when I thought of about a georeactor, I thought, well, this is an ideal energy source to power such a mechanism. But then later on, I got to thinking about convection. Oh, okay. If you heat something from the bottom, you see this in a lava lamp. You know what I'm talking about?
Oh, yes, I do.
From the 1950s, where it's heated from the bottom, the fluid goes to the top where it cools a little bit, and then it falls back to the bottom again. Well, if you insulate the top of it so it can't cool, it messes up the convection totally. See, convection only can take place if the bottom is hotter than the top. All right, so the bottom gets hot, it becomes less dense, it goes up, and then it comes down. Well, it seems that nobody seemed to have realized when they talked about the convection in the Earth's core, that the Earth's core is wrapped in a 2,000-mile thick insulating blanket of silicate rock. So convection or any other method of heat transport might bring heat from the bottom to the top, but it's not going to be efficiently removed. And so you can't have long-term convection in the Earth's fluid core. Now, the geomagnetic field undergoes reversals from time to time with an average time interval of maybe 200,000 years. But there are periods in its history where it has been extremely stable for as long as 40 million years. So that you can't have that kind of stability if the Earth's magnetic field is produced by a convection-driven dynamo in the Earth's fluid core, because you can't efficiently remove the heat. That's
now, will the Earth's core ever burn out? I mean, is that something that's eventually going to happen?
Well, when you talk about burning out, you're talking about not the Earth's core, but the heat source.
Right.
The georeactor. Okay? The Earth's core isn't being consumed. All right?
Okay.
It's just heated. So basically, the whole idea of the magnetic field being created in the Earth's fluid core, it can't be if it's a convection-driven dynamo like people think. Well, that got me thinking, what about in the georeactor? Now picture this. Imagine at the very center of the Earth, this little ball of uranium that's just fissioning away, producing heat. And imagine that that's surrounded by a shell of fission products, maybe other uranium, whatever, that's liquid, that's being churned around by the heat, that's being, and right above it you have the inner core, which is a thermal conductor, and above it you have the fluid core, which is a thermal conductor. So the shell around the core of the georeactor, the subshell, has heat at the bottom, and it has a heat sink at the top, a place to take away the heat. So that is the condition that you need for convection, to have a stable convection. And so a couple of years ago, I first published the idea that the georeactor is not only the heat source, but it's the production mechanism to produce the Earth's magnetic field.
Okay.
So
what actually controls the energy output? Is it the rotation of the Earth, or?
Well, I think the control of the energy output of the georeactor is. I'm trying to think of an analogy to do. Well, imagine if you had a pot of water on the stovetop, and at the top of it you had a cold surface. Okay. You if you heated the bottom too hot, all of the substance at the bottom would turn into vapor. But if you adjusted your heat just right, some of it would be at the bottom, still as the liquid, some of the water. Some of it would be at the vapor, and some of that vapor would be hitting that cold surface and condensing and dropping down. So you'd have a constant reflux between what was going up and what was coming down. And I think that's sort of the control mechanism to keep the georeactor from running wild. If it produces too much heat, it disassembles. It comes apart, and it quits fissioning, or that part of it that comes apart. So there's a dynamic. Now go ahead.
Oh, go ahead. I was just going to ask, now, does this georeactor theory apply to all or most planetary bodies throughout our universe?
Oh, that's a beautiful question. I love it. I published, I think it was last year. Either last year, I lose track of things here.
You got a lot of stuff out there.
It was either 2009 or 2010. What I was able to show is that there are only really two kinds of primordial matter. The really oxidized stuff, like the carbonaceous chondrites, where everything's combined with oxygen. This is the kind of material that could form by condensing at very, very low pressures, and maybe in interstellar space or in the far reaches of the solar system. And the other stuff is the highly reduced instantite chondrite material. And there's good reason to believe that condensed at high temperatures and high pressures. And that's why it's so oxygen poor. And in 1944, there was a chap who had the idea that the Earth rained out from the center of a giant gaseous protoplanet at those pressures. And he calculated the same sort of conditions that I calculated about the formation of instantite chondrites. And so there's good reason to think that there's only basically two kinds of matter, primary matter, in the solar system. And so what that means is that all of the planets that we know of that have big massive cores have the kind of matter that is oxygen poor. So yes, the answer to your question is a very important answer. You would expect a georeactor, if you can call it that, in planet Mercury. You can expect it in large planets. I mean, you can expect it in moons, large moons like Ganymede that has an active magnetic field. It's thought that the moon, our moon, once had an internally generated magnetic field, just like Mars.
Yeah, now that leads me to ask now, if these planets can generate a certain amount of heat and energy from themselves, and I wonder if it's possible that, like a planet like Mars, if I've heard theories of people living below the surface, would that be possible? A little out there, but
it's a little far out there. I'm trying to think of what's the Arnold Schwarzenegger movie about that. You know.
Yeah. Well, I've heard people such as, for one, Richard C. Hoagland, who's talked about life being on Mars and below the surface, and I've always wondered if that would be possible, saying that there's such a dense amount of oxygen on Mars. I don't know how it'd be possible unless they breathe something other than us, but I mean, I have heard the theories.
Well, I don't think that could be the case. I mean, there might be some microorganisms or something.
Mm-hmm.
And there's reason to think a lot of the water might be underground on Mars. But so far I've yet to see any good indication that there were people, or that any intelligent life.
I'd like them to send me a signal if they're listening.
Exactly. I keep thinking about this one science fiction story I read back when I was, I guess a teenager or something, about a spaceship trip to Mars, and they found something in the dust, and it was a gear wheel. And I thought, well, that's the kind of evidence that you really need.
Yeah, absolutely.
But no, I don't think so. But there's some serious thoughts people are having about how to make Mars a habitable place. And if you think about it, there's only one place in the entire solar system that we could potentially colonize. I mean, suppose that we had some knowledge that at some point in the near future the Earth was going to be destroyed or uninhabitable, rendered uninhabitable.
And I've heard of that too, so we'll get into that a little later.
Yeah, well, if you had to establish a colony, a self-sufficient colony, I mean, Mars is really the only place in the solar system that has the environment where that might be possible. But it would be a very, very difficult thing. I mean, we think of the past colonists on our own planet. They crossed the ocean in sailing ships and set up colonies. But those colonies were not all that far away, and in pretty much the same environment that their homeland was. So, I mean, we'd have to face immense problems if we attempted to colonize Mars.
Now, what about Europa? I've heard of oceans and such, and Jupiter being so huge like it is, and generating maybe the heat source possibly to sustain that planet. I mean, if there's oceans, wouldn't that mean there's possibility of maybe some kind of fish life there?
Well, the problem is I'm not sure that the oceans are just simply water oceans and not oceans that are mixed with all kinds of things that would be uninhabitable. I also be interested in what kind of energy sources. See, here's another problem. When I came out with the idea of nuclear reactors as energy sources for the giant outer planets, I spent almost a month writing a proposal to NASA to get funds to do research. And Paul K. Kuroda, who was the guy, remember, who had predicted the occurrences of nuclear reactors and uranium mines that were later verified at Oklo? Well, he agreed to be a co-investigator. But as he told me, he would do it pro bono because he didn't need the money. So I made the proposal to NASA. And of course it was evaluated by people who get their funding from NASA, mainly people at the Jet Propulsion Laboratory. And of course, to no surprise, it was ranked, I forget the exact number, it was ranked number 120 of 120 proposals considered relevant to their program.
Mm-hmm.
In other words, they did a number on it. And so ever since then, people at NASA have systematically ignored planetary nuclear fission reactors. And yet increasingly they find evidence that the moon is not as solid as they originally thought. Ganymede has a magnetic field. Europa has this ocean. There's evidence for energy sources. But NASA, being the political institution that it is, doesn't have the character or the integrity to look at it as a scientist would and say, hey, maybe Marvin Herndon is on to something. This should be investigated. This should be discussed. This should be acknowledged.
That's the problem. They don't do that, and you know, it seems like the drive for not only this country but the world. We should really be putting so much of our resources and energy into exploring what's out there, just in case one day this planet's not habitable. And you know, instead we just waste so much of our time with wars and everything else. And I think they overlook quite a bit. I mean, for one, deciding to do away with the shuttle and have to depend on other countries to go to space. It's just, I feel like we should have been to Mars by now.
Well, we should have. The problem is that we should have been at the top technologically, but in every field. But what's happened is that in America, the politicians have politicized everything, and organizations like NASA that get money from the government. I mean, everything is political, and where politics enters, science goes out of the window. Politics and science are totally incompatible. Have you ever heard that truth was absolutely necessary in politics?
Absolutely not.
Absolutely not. But I will tell you, truth is absolutely necessary in science, because science is about truth. It's about the true nature, discovering the true nature of Earth and the universe. And if you start making up stories in science, pretty soon people don't know what to believe. So you really want to... Go ahead.
Oh, I was just going to say that I think that global warming deal, I think that defaced quite a bit of scientists when they put out the reports of global warming. And I don't think, there's climate change, but I think a lot of people aren't buying into what they're telling us now. And, and that's another case of the government getting involved.
Yes, and see, that it's like one hand washing the other hand. The government provides the money for the scientists. Well, the
Mhm.
scientists say, oh yes, humans are responsible for global warming. Then the government in turn says, well, based on these studies, well, we have to, and they've done this. They've classed carbon dioxide as a pollutant.
Yeah.
I mean, think about it. You're a walking, talking pollution factory.
Yeah, it's going to cost me money just to breathe.
Yes, well, then they can regulate it. Then they can sell carbon credits. They can do all this stuff, and it's based on nonsense. And so this is the real. There's two problems. There are two elements that seem to be totally missing in this country. One of them is integrity, and the other is truthfulness. And it just seems that everybody is out to get what they can at anybody's expense, and irrespective of the consequences. Now that's not right. It's not the way you would. It's not the way you would run a family. It's not the way you treat your own family, and it's leading us to a path toward destruction, and we're getting weak. We can't compete scientifically with, for example, Europe. China's coming out with some pretty serious science.
Yes, they are.
I remember in 2004 I was invited to give the Christmas lecture at the Institute for Trans-Uranium Elements, which is part of the European Commission in Karlsruhe, Germany. And I remember thinking, after I had seen their facilities and what they were doing and so forth, I felt like I was coming back into a third world country coming home. I mean, scientifically.
Isn't that sad?
Oh, it is very sad. And it's very sad. And the whole idea of funding, of the government funding science, was done with the idea that it would improve technology, it would improve universities, it would make America independent intellectually. Then along came the National Science Foundation, founded in 1951, to support civilian science. Well, when Congress founded the National Science Foundation, NSF, I guess the senior people involved wrote the rules about how they would fund science. And they made some serious mistakes. I mean, for example, one of the rules is that the scientist would propose projects, and that those proposals would be peer-reviewed. In other words, they would be reviewed by the scientist competitors, the same people seeking money from the same pot.
Oh, boy.
That's not bad enough. The reviews were done in secret. Now, if you have any sense of what happens in any society where there's secret, whether it's the infamous Spanish Inquisition, or Ceausescu's Romania, or Pol Pot's regime, wherever there's secrecy, corruption abounds, and people become fearful. They become fearful.
I think you've just described the government.
Well,
the secrets.
This is really true. And so suppose you're a scientist, and suppose that your whole career, your livelihood depends upon writing research proposals to get funds to do research. Now, if you write a proposal, say, look, have good reason to think that the excess heat from Jupiter is caused by planetary nuclear reactions. Everybody missed that. but I didn't. Okay, and you write a proposal like that, and you submit it to NASA, and you know your competitors will kill you, and I can document that. So what do people do that want to get supported? They sing the same songs, they chant the same chants, just like in any kind of a totalitarian regime. They don't want to stand out. They don't make discoveries that contradict what other people are doing. If the politically correct thing is human-produced global warming, oh, by God, global warming is caused by people using too much carbon and filling the atmosphere with carbon dioxide. And
all right.
Yes, just send me a big check and I'll do some more work on it. But if you said no, the amount of carbon dioxide produced by humans is insignificant compared to all of the changes in, for example, the sun. The output of the sun is variable, or the heat coming from the inside of the earth is variable. Well, you don't write a proposal and say, hey, the people who make those models ignored those changes. Well, you wouldn't get funded. You wouldn't get your papers published. And you see, so
you pretty much got to be a politician and tell them what they want to hear to get what you want.
That's exactly right. You don't step on anybody's toes. In other words, and that's not science. See, science is about finding out what is wrong with present thinking and correcting it. That's how you make progress. If you think back in terms of any revolution in science, it's because somebody came along and said, hey guys, we've been doing it a little bit wrong. Here's a different way to do it that leads to improvements in understanding and new knowledge. So this is what you can't do if you've got government funding. And so this is the reason that science is not being done. Real science.
Okay. Doctor, I want to take a break. We're going to take about a 3-minute break here, so if you need to get a drink or what have you, now will be the time to do that. Yeah, it is. It was so interesting. I didn't want to cut you off earlier, but I will take that break now. So you just hang on the line and do what you got to do, and yeah, we're going to be about
on the line. I'm going to go get something to drink. I'll be right back.
Okay. All right, everybody. Yes, sir. The number is 347. Oh, go ahead.
I'll say hello when I'm back on the line.
All right, that's fair enough.
Thank you.
All right, everybody, we'll be back in just a moment. I'm Michael Vera. This is Late Night in the Midlands, and my guest is Dr. J. Marvin Herndon, and we're talking about several things, Earth's inner core, and we're going to get in even deeper about more of the planetary stuff and even talk somewhat about the oil in the Gulf. Dr. J. Marvin Herndon, and I believe he's back with us. Doctor?
Hello.
Hello. Okay, yeah, before we go any further, why don't you go ahead and give out your websites while we're at it.
Okay. Are we all set here?
Oh, yes, sir, we are.
All right. My website is nuclearplanet.com.
Okay.
That's nuclearplanet.com. The reason that name came about is in August of 2002, Discover magazine featured my work as the cover story about a nuclear reactor at the center of the Earth, which was a big break for me. It got the word out to a lot of people. The name of the article was Nuclear Planet. Very good article written by Brad Limley, Nuclear Planet. And so I thought, well, that sounds like a mighty good name, and it hadn't been taken for a website. So nuclearplanet.com became my flagship, so to speak. This is where I try to post easy to understand descriptions, as well as many of the scientific papers. So you can look at that at different levels of depth. And
oh, I'll be honest with you. I spent probably a good 5.5 hours today going through quite a bit of that stuff, reading through it. There's a lot of great information. It really is.
And even some stuff about the suppression of science. Suppression of science by the National Science Foundation, the Department of Energy, the American Astronomical Society. These are rather much case histories. See, here, let me explain something about science so that your listeners will understand.
Okay.
Science should be an open forum. So I come along and I publish a paper where I say, for example, that here are the reasons that the inner core of the Earth is nickel silicide instead of nickel iron metal, and I list the reasons. Then people in the scientific community have the obligation, if they can, to prove that I'm wrong or to prove that I'm right. And if they can do neither, then at least they have the obligation to acknowledge that idea along with the other ideas that may exist.
Exactly.
And this is the way science works. And so when I publish a paper, I fully expect the members of the scientific community, if they don't like it, they should find out what's wrong with it, and they should refute it in the open literature, preferably in the journal where it was published. But people don't refute my work. And it's not surprising, because I was trained by very, very good scientists, and I was taught to do science in a pretty serious way, so it's not too likely they could tear holes in it. But they ignore it. And that's not good science. So this is what science is really about. Somebody comes up with an idea that's based upon some logical progression of observations, and then it's out there, and other people should attack it and find out what's wrong with it. And if they can't, then they should maybe they could find out that it's right. But in any case, they should acknowledge it until it's been thoroughly refuted, and then it can just.
Well, unfortunately, they get it set in their mind, and they only want what they want, and they don't look at the other possibilities.
Well, there's another problem out here now. It's really hard to make a discovery. I mean, it is really hard to make a discovery. But what people do instead, and this has become popular since about the 1960s, is people make models based upon assumptions.
Mm-hmm.
And, you start with an idea. Okay, I'm going to make a model of Earth forming from a bunch of meteorites colliding and balling up into stuff and making a planet. Well, they make models. Usually they're based on mathematics or computer, and they make us a bunch of assumptions right from the get-go. And then the model ends up making the Earth the way the model intended to make it Earth. I mean, this is what a model is about. You set up to make a model. Of course, you have to make it do what you're setting up to do. It's a self-fulfilling prophecy. And it's
so it's not written in stone. It's just basically it's an idea that they've come up with, and of course, if they've created this model, they've created it to do what they thought would happen.
Exactly, and it doesn't necessarily, even if the model looks like it works, it does not necessarily mean that nature behaves that way, or that events in the past produced that sort of result.
I've often thought that way with like hurricane models. You know, when they say, well, it's going to go this way or that way. And when I lived on the at South Carolina, I never bid on that. I said, you know, it could do anything just because they say it should go that way. What's that?
Where in South Carolina?
I lived in Columbia, South Carolina, but the last couple of weeks I had moved back to Rochester, New York. So, but I was in Carolina for a few years, and unfortunately, you know, I always look forward to seeing a hurricane come in. I know it sounds crazy, but I've never seen one, so I never got that chance.
Well, I was born in South Carolina, and and as a young child, I did watch hurricanes come in, and I one time, I guess in high school, I went out with the rescue squad and really got some up close views of hurricanes. But anyway, getting back to models, there's an economist, a well-known economist named George E.P. Box, B-O-X. And I think the thing he's most famous for was for a statement that says something like this: all models are wrong, a few are useful. Well, those might not be his exact words, but they're very close to it. And hurricane prediction models come into the latter category, to possibly useful. Okay,
right.
Because if they could improve them, and you know, here's a model where you constantly are getting new data. So and hurricanes keep occurring. So in principle, you should be able to improve the model over time,
right,
and better predict the path of a hurricane. Now that's a useful model. But to make a model of an event that took place at one point in time, like the formation of the Earth, and just begin it with assumptions, that's the wrong way to proceed. One has to proceed by, or one should proceed by beginning with the abundances of the elements and beginning with the properties of matter. I mean, matter behaves in a certain way. And if you understand the way the matter behaves, then you can begin to piece together how the Earth formed.
Now, do you buy the whole Big Bang theory? Do you think that's how it all came about?
No, I don't buy it at all.
Yeah,
I don't buy it
either.
at all, and I'll tell you why. I think that there are pieces missing. Okay, if you, I learned a long time. You know, the masters I told you I learned from. One lesson from one of the masters, Hans Seuss, that I learned. He once told me. He said it's more important to know what's not known than to know what is known. Okay, and I think that also pertains to the whole idea of the Big Bang. People make these models based upon what is known, or at least what they think they know, and ignore the things that they don't know. And they then do very complicated calculations and based all these inferences on mathematical results. And yet, I think there's some underlying assumptions that are not correct. In fact, I speculated on this very subject in my book, Mavericks, Earth, and Universe. It's sort of an easy-to-read book. That begins with, basically it sort of begins like we started talking tonight with the Earth because it's all a logical progression. But then when I get toward the end, I then look at the thermonuclear ignition of stars and the formation of galaxies and why galaxies have the distributions. And then I end the book with some speculation about the universe as a whole. And I think that's the right word. I think the Big Bang theory and anything else is a speculation, because that's
yeah, it's almost needed to be there kind of thing to know for sure. You know, it's first, because some of these people, they seem pretty confident, and it's like you really don't know for sure. It's another case of that model thing, like you were just talking about.
Yeah, it is. It is very much, but it's a model that's based upon some limited observations, and some observations that are interpreted one way when perhaps there is another way to interpret it. Let me give you an example.
Okay.
I'm trying to think of the chap's name. But anyway, back in the 1930s, when people were first learning about radioactive decay, I think it was Wolfgang Pauli. When people were first looking at how atoms decay, and one way is they shoot out an electron. It's called beta decay. Well, people made measurements, and they found out that if they take into consideration all the different energies of the particles, the electron shooting out, the recoil of the atom, and so forth, there's some energy missing. And that was a great mystery. And I think it was Wolfgang Pauli who came along and said, well, this is energy must be being carried away in an invisible particle, one that we can't measure.
Mm-hmm.
And so, see, he was examining the whole picture, and he was saying something's missing. And he stuck his neck out and said, well, there must be something carrying that energy away, an invisible particle that was called the neutrino. Well, guess what? Lo and behold, some years later, people discovered neutrinos, were able to detect them. So, and neutrinos are very much a part of beta decay. So, the principle here is you can't understand a system necessarily by just seeing what you know to be true. You have to think, well, maybe there's some other things that you don't know about that may be coming into play. And if you're real clever, maybe you can figure out what those are, like Pauli did.
Right. Now, what would happen if the Earth's core had stopped rotating? Somebody wanted to know.
Okay. Well, first of all, the Earth as a whole rotates. Okay. The inner core, it's been found to rotate slightly faster, but only faster that it was in the sense that it would make one additional revolution in a year, which isn't very much.
No.
Okay, since the planet as a whole makes one revolution in a day, or one rotation in a day, the inner core would rotate just ever so, maybe 1 degree out of 360 more in a day. So essentially, if the planet stopped rotating, that's the question, not just if the core did. If the planet stopped rotating, what would happen? I think the first thing that would happen is that the Earth's magnetic field would collapse. And the reason is, as far as we know, the only viable mechanism that people have come up with for creating the magnetic field is like this dynamo, the magnetic amplifier. And that depends upon convection motions, heating at the bottom, cooling at the top, in a rotating body, which causes those to twist around. You picture that?
Oh, yes.
The planet Venus doesn't seem to have a magnetic field. And so one of the thoughts is that planet Venus has a very, very slow rotation rate. I forget what it is, one rotation a year or something. It's very slow.
Mm-hmm.
And so the thought is that the reason that it doesn't have a magnetic field is that it's in the slow rotation. Well, I think that the first thing that we would see if the Earth quit rotating would be the collapse of the magnetic field, and when that collapsed, the solar wind would come streaming in, because the magnetic field is the Earth's magnetic shield. It deflects the solar wind safely around and past the planet.
So it's our force field.
Yeah, it's like, hey, in all the science fiction movies, right? Energize the deflector shields.
Yes.
Well, this is the case. So what would happen is the solar wind would come streaming in. And so I don't know whether, have you ever seen the aurora borealis, the northern lights?
Yes, I have. I've seen them once in my life.
I saw them when I was a young teenager in Washington, D.C., which was a rare sighting. And it was only like red flashes. It wasn't the spectacular displays that you see in the northern latitudes. But
see, I've seen them in Syracuse, New York, and a very rare occasion there, too. And, wow, I was near a lake, and I never seen nothing like it in all my life. It just colors everywhere, and wow.
Isn't that amazing? Oh,
it is.
Incidentally, since you mentioned that, let me mention on nuclearplanet.com, somewhere down toward the bottom of the home page, there are links to YouTube videos that I did, and one of them is entitled "The Origin of the Earth's Magnetic Field." That video begins with the most incredible picture of the aurora borealis. So you guys should look at that, and it also explains what I'm trying to talk about. But anyway, getting back to the Earth's rotation has stopped. What would happen is the solar wind would come streaming in. Now, in one sense, it must be absolutely romantic and picturesque. Imagine being on a beach in Hawaii or some Caribbean island, palm trees, a beautiful tropical background, and then the night sky ablaze in all of this splendor. Hey, that would be an incredible scene. And that's what you'd see if the Earth's magnetic field just shut down. Well, you also would see some bad things. Satellites.
I was going to just say that.
Well, that's the way of the world. There's a price for everything. And the price is, the bad part is that the satellites, their electronics would be fried. Everywhere there were long wires, like electrical transmission grids.
Right.
Electrical currents would be induced in those and would burn out transformers. Even currents would be induced in pipelines and in railroad tracks. These things could start fires, especially it'd be dangerous wherever they come to a point. The charge would be intensified. And so these are really serious things, and these effects have been observed. The Earth's magnetic field deflects most of the solar wind, safely around and past the planet. But every once in a while there's a solar storm that gives a more intense than usual burst. And that sort of overwhelms the field. And that's when you see, for example, the displays of the Northern Lights in New York. So these
which is very unusual there. You see a lot of stars and a lot of clouds at times, but Northern Lights is, like I said, it was a once-in-a-lifetime thing for me thus far.
But you'll never forget it.
Never forget it. It was amazing.
Yeah. Well, the thing is that when those things happen, occasionally the currents are induced in power transmission systems and will take out transformers and damage equipment, and that's documented. So that we know that'll happen, and it would happen on a really big scale if the Earth's magnetic field were to stop operating. Now, the other consequence of the Earth ceasing its rotation, standing still, well, you might think that that there's a flying saucer hovering in Washington, D.C. If you remember the really great movie from the 50s, The Day the Earth Stood Still.
Oh, yes.
You remember that one? Oh, that's a classic.
I sure do.
But also, you would have a problem because half of the Earth would be baked in sunlight 24 hours a day, and the other half would be in darkness. So there would be no night and day. It'd be either day or either night, depending on where you were. So that would be an unpleasant situation, I think.
Yeah, so it would really stink on either side, I guess. Well, one side you're going to be freezing, and the other side you're going to be cooking.
But there is this romantic picture of palm trees and northern lights. Somehow, oh well.
So you see the transformers exploding.
Exactly. Well, if do you have any? Has anyone else called in with questions? We had a couple of calls. They're sitting on, and what I'm going to do is, because we've only got probably about 10 more minutes for this first 2-hour segment, I'm going to open the lines in the third hour for anybody who wants to call in and ask a question. Okay. So what we're going to do is, in about the next 10 minutes, what I'll do is I'll disconnect with you, and then my screener will get you back on, because we have to break down and then go into our next 2 hours. But another question I had for you really quick is, now that we're talking about the magnetic field, is could it reverse? Oh yes, and this is interesting. This is interesting because the reversals have been observed. Also, very stable operation has been observed, like I say, for 40 million years. So how can that happen? And I think it happens this way. Imagine there's a connection between the sun and the center of the Earth. Okay, the sun streams these charged particles past the Earth, and the Earth's magnetic field deflects them. Now that's a magnetic circuit. You can think of that as a magnetic circuit. Now, in a magnetic circuit, which is connected to the georeactor, now in a magnetic circuit, induction, which is transferring energy, only occurs during change. Okay? If you were, for example, you're familiar with a transformer.
Yes, I am.
If you were to put a meter on one side of the transformer and hook a battery to the other side, what you would see is the meter would get one kick and drop back to zero. And when you disconnected the battery, the meter again would kick back to zero. And that's because you only induce change in a magnetic circuit when there is a change going on. So if the streaming charged particles from the sun are very constant, there'll be nothing induced into the georeactor. But imagine a really intense burst of charged particles. That would induce an electrical current in the georeactor, which could disrupt the convection.
Now, what would happen if it had reversed? How would that affect life as we know it here?
Well, that's a really big question, and a lot of people have speculated on it. And I guess it really depends to a degree on how long the period of reversal is. There's one group of people measure the remnant magnetization in rocks, in lavas. If a lava flow cools in the presence of a magnetic field, it's like little recorders that record the direction and sometimes the intensity of the magnetic field at the time that the lava cooled. Well, there's a group at the University of California at Santa Cruz who have measured the magnetic field in layers of lava that were laid down very quickly during a reversal. And they found that the magnetic field changes 6 degrees per day. So, I mean, if a reversal is 180 degrees, then you're looking at 30 days for a reversal to take place. Really, this can take place very quickly. And it's probably not just one switching. It's probably back and forth and a lot of irregularity until the system stabilizes. What would happen to people? That's a real good question, and I don't know that I know the answer. I think
it would probably mess with animals pretty bad, wouldn't it?
The ones that navigate on the magnetic field, and that would confuse them big time. And I don't know how it would affect us personally, or whether it might, or whether the charged particles coming in could. It's hard to know. I don't think a whole lot of work's been done. But there's something that's a lot worse than just what happens during a reversal, and maybe we can talk about this in the next hour, and that is what happens when the georeactor burns all of its uranium and the Earth's magnetic field collapses. I
was just going to say that's actually something that I was very interested in talking about. What does happen when it collapses?
Yeah, well, get me started in the next hour, or do you want a brief one right now?
Oh, no, we can get started in the next hour. What I'll do is you go ahead and give out your websites once more. And, again, my screener gives them out in the chat room as well, and I'll have them on my website as soon as tomorrow. But go ahead and give those out again, and then what I'm going to do is we're going to hang up with you, and then at the start of the next 2 hours, my screener is going to get you back on so you can get another break in.
Excellent. So you'll phone me back again.
Absolutely.
Yes. Well, the website is nuclearplanet.com. nuclearplanet.com.
Mm-hmm.
And there's a lot of stuff there. There should be something for everyone, including a little bit for teachers. Some items of interest, and I think the teachers will enjoy that. So
okay. All right, great, Doctor.
Let me explain. The people look up in the sky and see a shooting star. Well, that's called a meteor. But some of those survive their fiery entry and land on Earth. And after they land on Earth, they're called meteorites.
Mm-hmm.
Well, meteorites formed at about the same time the solar system formed. And they generally formed as fairly small bodies and didn't get a lot of geological activity like the moon, for example, or the Earth.
Right.
And so some of those meteorites contain almost the original set of elements that the solar system started with, and that's like a Rosetta Stone. I mean,
Mm-hmm.
here you can hold in your hand something that was a very good sample of the sort of matter that the solar system formed from, minus the gases, of course. The gases
Right.
like hydrogen and helium didn't get preserved. Well, so you would think that, well, gee, if you have a meteorite, you could look at it and discover that it must be like a planet, because all these things came from the same pot of matter. You know, they're just like from one big vat. And it all sounds very simple until you start looking at it, which is usually the way things are. The devil's in the details. There are a group of meteorites called chondrites that have the same elements in almost the same proportions as you can determine in the surface or in the photosphere of the sun. Again, except for the gases. So because of that, we have a good sense that this is like a representative of the primordial composition from which the solar system formed. The devil in the details, though, is there.
Dr. J. Marvin Herndon. We're going to talk about the Earth's inner core. Let me tell you a little bit about Marvin. Dr. J. Marvin Herndon is a scientist with a strong and yet broad background. Originally trained as a physicist, he earned a Ph.D. in nuclear chemistry and received postdoctoral training in geochemistry and cosmochemistry from world-class master scientists who had themselves learned from masters. His website, nuclearplanet.com, contains easy-to-understand descriptions of his work. The first thing you find on that website is his statement: the purpose of science is to discover the true nature of Earth and universe, and to share that knowledge with people everywhere. That's what I do, and indeed, that's what he does. 3 decades ago, Marvin Herndon began to discover that the inside of the Earth was not quite like what government-funded scientists have long thought, and quickly came to realize that scientific independence comes at a price. Since then, he has pursued science independently. Dubbed a maverick geophysicist by the Washington Post, Marvin Herndon has lived up to the moniker by providing entirely new insight into the nuclear georeactor origin of the Earth's magnetic field and into the new understanding of the way the Earth formed and works, called Whole Earth Decompression Dynamics, which provides new insight into where and why oil and natural gas deposits occur. Ladies and gentlemen, please welcome my guest tonight, Dr. J. Marvin Herndon. Good evening, sir. How are you?
Hi, good evening, and what a great introduction.
Well,
Gee,
thank you so much.
You've said everything. I don't have anything to say now.
Well, it's going to be a long 4 hours then.
Oh, no, I'm really only kidding. What I would like to, 3 groups of chondrites, and they're different. And this has posed a real problem. There's one big group called ordinary chondrites, and they get the name ordinary because they're the most common of the meteorites. And back in the 1930s, 1940s, people began to think, well, the Earth must be like one of these common meteorites, ordinary chondrites. And that thinking has persisted to the present. But there are two other rare type of meteorites, not nearly so common. One of them is called carbonaceous chondrites. And there's a lot of discussion about the organic matter in them and whether they might have at one time fostered life somewhere. But they, all of their elements are combined with oxygen. So we know that they can't make a planet like Earth because we know Earth has a big, massive core.
Right.
And all of the inner planets do. So it can't be that group. There was another group. It was called instatite chondrites. And these formed under conditions where oxygen was really starved. They're much less oxidized than the ordinary chondrites. And some of the minerals aren't found that are contained in them aren't found on the surface of the Earth. Like a mineral called oldhamite, which is just a compound of calcium and sulfur, calcium sulfide. Well, you don't find that on the surface of the Earth. It reacts with water. So people thought, well, gee, these have strange minerals. So they're not like what's on the surface of the Earth, and there aren't many of them, so we'll ignore them. Well, ignoring things in science is kind of like bad business. So anyway, back in the to say right up front at the get-go, is that I'm open to answer any kind of questions you might have, not just about the inside of the Earth, but about what science is all about, and you know, just whatever I can shed a bit of light on, because that statement's true. Science is about discovering the true nature of Earth and universe. And
it sure is. And
it's important to share that with people everywhere. So I appreciate the invitation to be on your program, because you're helping me do that.
Well, I appreciate what you do, and I definitely appreciate you taking time out to be with us. I've been looking forward to this. I've gone through your websites, and I'll tell you, you've got a lot of great information there. Definitely not something you can read in one night. There's quite a bit there, a lot of great information. And we're giving out them websites in the chat room as well, just so you know. And at the end of the show, I will get your links up on my websites as well.
Excellent. I appreciate that.
Oh, absolutely.
It might be a good idea to tell you how it is that I got to be to get on the path that I ended up on.
Please do.
When I was a graduate student, like any new graduate student, you know, you look at what the professors are doing and what interests you, and most of them weren't doing anything I was interested in, except one, a chap named Marvin Rowe, Professor Marvin Rowe at Texas A&M University, and he worked on meteorites, and in fact he made some important discoveries related to meteorites, and that just seemed to click. That was the beginning, and I later came to understand why it is that meteorites are important. You know, 40 or so, the idea was really sealed that the Earth was like one of these ordinary chondrites. Now, let me give you a brief sketch about what the Earth is like.
Okay.
In 1898, Emil Wiechert realized that the density of the Earth is too great for it to be made entirely of rock. See, people thought it was rock because everywhere you look is rock. Even underwater there's rock. But he realized, based on measurements made 100 years ago, that the density is too great for the Earth to be just made of rock. So he thought that maybe there's a core inside of the Earth, like the iron meteorites he had seen in natural history museums.
Mm-hmm.
Well, only 8 years passed before the core was actually discovered by a seismologist, Thomas Oldham, who had actually he was studying how earthquake waves travel as they go deeper in the Earth, and they seem to get faster and faster the deeper they go, up until he discovered they come to one point and then they slow down a lot. That was the discovery that the Earth has a core. That was in 1906. And in the next 20 years or so, the dimensions of the core were pretty well figured out for more precise measurements, and it was found to be liquid. So the picture that came out then, say about 1930, is that the Earth was like, a big ordinary chondrite with a core. Go about halfway to the center and come to a core, and it's liquid.